Some of you may know my work on agent-based modeling. So here's a chapter on it in case you want to know more. We'll go quickly through many subjects, but there are always links to the original work where you can find the details, and I will share my slides. So if you still have questions, just send me an email, okay? Now, importantly, what we've been trying to do is to bring together data science with theory, with experiments in laboratories, or also online, or real-life experiments. And we have also at times created participatory platforms. So bringing together analytical, theoretical work with empirical data or experimental data and applications is what I'm interested in. And of course, it takes many years to go through this process. But in the meantime, you know, I've accumulated all those years. I started with pedestrian flows. There are a lot of coordination problems that every one of us faces every day as a pedestrian. So it's a system that we all know very well. And unfortunately, it's a little bit wrapped, this presentation. Anyway, so let's switch to the next slide. What I've been interested in is actually self-organization in pedestrian crowds. So if you watch pedestrian crowds, then you'll find that there is, in this case, the self-organization of lanes of uniform walking direction in counterflows. So here people walk on the right-hand side. I don't know why it doesn't actually play it smoothly, but you'll find the videos also at YouTube. So this is not necessarily what you expect because there's no law telling people how to walk. There's no police telling people what to do. And even most people are not aware that they're doing this, that they're creating those lanes. So it's really an emergent effect. Something new happens when many people interact with each other. Okay. Now you can simulate that. We've done this. Unfortunately, it's also not playing smoothly, but again, these kind of videos are online. No idea what the problem is, but it may be Zoom or another process in the background. So we do understand how these lanes come about. This starts out with about 4 or 5 lanes, then eventually it will be 3, and in the end it will be 2 lanes. I think we're about there in the meantime. And how is this being simulated? One way of doing this is actually by means of the social force model, which has been inspired by physics, but it goes beyond physics. It assumes an equation of motion. It's kind of trivial, but additionally, there's an acceleration equation that's made up of a sum of several terms describing different motivations of pedestrians, like walking with a certain desired speed. And so there's an adjustment of speed to the desired speed, and there are interactions between pedestrians in order to avoid collisions, and interactions also with the environment. Okay. It's not just lane formation that we find. There are many other self-organization phenomena. For example, at bottlenecks, we find oscillatory flows. It's as if there was a traffic light controlling the flows. But in fact, there is no traffic light here. It's just pressure builds up on one side, and that stops the flow from the other side, and eventually the tide turns. And so it goes back and forth based on self-organization again. And there is a third phenomenon, collective pattern of behavior that I'd like to show you, which is stripe formation, a generalization of lane formation And this enables people to walk through a stream of people without even stopping. Now, if I would have asked you to figure out a way to efficiently walk through another crowd, would probably have sit down for a long time. You've figured out mathematical formulas, and I don't know what solution you would have come up with, but this just happens, you know? And so people basically walk forward with those stripes, and they can walk sidewards within the stripes, and that's how they're able to basically penetrate that wall of people walking into another direction. It's totally amazing what people subconsciously can do. All right. There are also self-organization phenomena in traffic flows. And those are the kinds of self-organization phenomena we don't like because they typically come with congestion patterns. And there's not just one kind of congestion, amazingly so. There are many different kinds. You know, it's like many different animals in a zoo. And the question is, how are they related with each other? What are the conditions under which we find this congestion pattern or that or that or that? Now, can we understand it? Can we simulate it? And in fact, we can simulate it. So this is simulated with simple models. Both microscopic and macroscopic models can reproduce these elementary congestion patterns for different flow conditions. And one of the models that has been used in order to reproduce those findings is the so-called intelligent driver model. And again, it has an equation of motion and an acceleration equation, just a few parameters in it. And it really describes the behavior of cars quite realistic. So if you have a car drive according to those equations, it feels quite natural if you choose good parameters. In fact, that was also the basis of driver assistance systems that we've built with a car company. Okay. Now it gets ever more difficult to switch slides. These are so-called phase diagrams. So they basically predict what kind of traffic you will find for certain flow conditions. So you have here the upstream flow on the freeway. You have here the on-ramp flow. And you can see have free traffic flow for low overall traffic volume. And up there are different forms of congestion. And if there are large perturbations in the flow, you would have even these additional congestion patterns. It would invade into this area of free traffic flow. And it means that there's history dependence, right? So the initial conditions have a say in terms of what will be the final outcome. There's multi-stability in that system behavior. So for a scientist, this is all very interesting and exciting, you know. For people producing this, it's pretty annoying, of course. Importantly, the theoretical predictions are confirmed by empirical data. So we have proof that we understand the process. Prediction was there also before the empirical analysis was done. So it was kind of a really predictive model that we have created. And we also have an analytical understanding for the conditions under which we find those different traffic patterns. Some call it traffic physics, but don't mind the name. The important point is that traffic congestion is predictable to some extent. The onset is hard to predict because it may depend on a truck overtaking another truck, and we don't know the exact moment in time when that will happen. But once it has started, we can predict the extension of the traffic congestion, and we can also predict the delays with high accuracy. Okay. Now, importantly, what we need to know is that in those systems with many components that interact with each other, in this case, many pedestrians or many cars, we have complex dynamical systems. And those complex dynamical systems have some interesting properties that most people in the world don't know about. For example, in this experiment over here, cars were supposed to drive in a circle and avoid accidents, of course. They were trying to drive smoothly. Instead, they produced a so-called phantom traffic jam. So small variations in the speed amplified eventually to produce congestion. And we call that phenomenon a systemic instability because it happens even though nobody wants it to happen. You know, we have intelligent people, well educated, with a driver's license, good sight, cars that basically give you perfect control. Still, everyone loses control. And that's what we call systemic instability. And there are many problems of this kind in the world that are still unsolved because people are trying to solve those problems without knowing about complexity science. This includes crowd disasters. This includes unstable supply chains, booms in recessions, spreading of crime, tragedies of the commons, and also conflicts, wars, and revolutions. All phenomena of systemic instability, all phenomena where you should know about complex dynamics. Okay? But complex dynamical systems are not our enemies. Our brain, our immune system, ecosystems, and societies are all complex dynamical self-organizing systems. And we would say these are good things. Living systems, the wonder of life, are based on self-organization. These are not centrally controlled. It's also not just chaos or anarchy. So what's going on there? Well, importantly, we need to know their limits of predictability. We know that from weather forecasts. Even if we had 100,000 times more data, we could not predict the weather on Saturday afternoon in 100 years from now. And why is that? Why am I so confident? Because there is a physics of how weather changes, and it's based on turbulence. And we understand turbulence to quite some extent. And it implies that very little changes can have large impacts over time. So just wait long enough and then something else happens. And we know that also from chaos theory. A very famous example is this deterministic attractor over there. And we sometimes speak of butterfly effects to basically symbolize that a minute change, like the flapping of the wings of a butterfly, could change, for example, the weather in the months from now. It's really very hard to imagine. I admit this, but mathematics proves that this is the case. You know, so we start very similar in the beginning, but eventually something very different happens. And now people may find this annoying, and there's some people who suggest to control chaos. And in fact, there is a field that's called chaos control. No, it's not anymore switching. And you see an example over here. So here's chaos, and these are controlled areas. Here's when one instance controls the chaos. Here's when two instances competitively try to control the chaos. Now, it seems to be good news, it's possible, but on the other hand, actually, controlling chaos doesn't mean it's an efficient solution. The chaotic solution could be more efficient. Think of markets, financial markets, for example, right? It would be a disaster if somebody would control them. They wouldn't work anymore. All right, still, many people really want to control complex dynamical systems. And here's a simple example. ecological system pre-equations, you get these oscillations in the population sizes of, say, foxes and rabbits. And let's say there is a hunter who wants to achieve an equilibrium like this. What happens instead, however, is that the system goes over there. So it does something else from what the controller wants to achieve. Now, assume somebody would want to control the entire world using a huge AI system that knows everything about how the world behaves and then tries to control by adjusting millions or billions of parameters. Well, most likely, that's my expectation, at least, you get tons of butterfly effects. And here's an example. We have been seeing work on autonomous cars for a long time. And recently, people are starting to question those systems. So are those adaptive cruise control systems spring stable, or do they produce congestion? Now, it's not good enough if it produces comfortable driving experiences for an individual driver if it produces congestion, right? There's even people who have formulated a requiem on the positive effects of commercial adaptive cruise control systems. Like that's the death sentence almost of this entire technology if there were not a solution to it. And we did that actually more than 10 years ago. And it's an adaptive cruise control system that is not trying to control every car centrally. Instead, it does something else. Probably this. Oh, now it's playing. Interesting enough. Okay, so what we're simulating here is stop-and-go traffic, just to show you that we understand the process. We have the equations. We can do the computer simulations. It looks kind of realistic. It's already a few years old, so you could do that more posh today, of course. Now, we're taking a helicopter to see what's the reason for that stop-and-go traffic. It turns out there is an on-ramp where cars are trying to get on the freeway. That produces small disruptions, and those disruptions will amplify, and it produces stop-and-go traffic. Now, eventually, we'll switch on a driver assistance system. In a certain percentage of cars, could be just 40% of cars. And those cars would basically automatically react on measurements of distance and relative velocity, like laser sensor or radar sensor. So 40%, say, of cars are equipped and do autonomous driving, and eventually you see the traffic jam disappears, even though the same number of cars enters the road per hour, right? So what did we do? We basically introduced real-time measurement and real-time feedback to change the interactions between cars a little bit. That's all. No centralized control, just we change the interactions. And so the idea is that with the Internet of Things, 300 years after Adam Smith, we finally can make the invisible hand work by using mechanism design, by learning how to change interactions a little bit so the system would do by itself, based on self-organization, what we want it to do. We don't force it. It will do it by itself, okay? So complex dynamical systems tend to self-organize. That means to do what they want, but establishing suitable interactions will produce desirable outcomes by itself. So this is basically my proposal how to do it. Now let's switch to urban traffic. We tend to have overregulated traffic today in many cities. And I'd like to propose a new paradigm to go from control to coordination. And such a circular traffic is an example, but there is really a nice video, again, unfortunately not playing smoothly, which shows an intersection in Egypt, which perfectly self-organizes, even though there are cars and lorries and there are donkeys and horses and pedestrians and bikes and motorbikes and everything, like highly diverse traffic. And the reason why it works is that we have a certain design that supports this. We have unidirectional flow in the front, we have unidirectional flow in the opposite direction in the back, and we have a small buffer in here, which allows everyone to adjust the speed in such a way that you have a gap when you want to cross. That's all. Give the opportunity for adaptation, you know? That's it. And so the question was, can we come up with a self-organized traffic light control, with a self-control system? And this is what we managed to do. So here it's, of course, a simplified Manhattan grid. And what you find over there is green waves, but green waves that have not been imposed on the system, but that come about by self-organization again. How do we do this? Basically, we measure not only the outflow from a street section, we also measure the inflow, and that allows us to predict how many cars are waiting in that queue at one time, and how much time would it take to clear that queue. Okay, then we have compared 3 different control systems. Kind of the classical centralized control, where we have a control center that tries to get as much data as possible, and then tries to come up with an optimal control, but it's an NP-hard control problem, so you cannot go through all possible solutions really. But it's a benevolent dictator approach where the center tries to coordinate processes throughout the entire system. And then in the middle, we have another approach where each intersection responds just to the traffic next to that intersection. So traffic flow controls the traffic lights rather than the other way around. And here's a system where we do the same thing, but if there's a long queue, we first clear it before we go back to travel time minimization, okay? And traditionally, we would think this should be the best because it coordinates the entire system. That should be the second best. And that one which is friendly to your neighbors is the worst because you give up your own benefits, basically. Then what happens is the following. This is for the benevolent dictator, pretty expected increase of queue length with the increase in capacity utilization. Now, for the second approach, the selfish optimization locally, we have a much better performance initially, but then eventually the waiting time explodes. So basically the system breaks down and traffic control center would say, see, this is why you're paying millions every year for us. But then the third approach, surprisingly, is better all the way. Even though it combines 2 rules that don't manage to improve traffic flow. But the combination does it, okay? Very unexpectedly so. And this has been tested in the meantime in several cities, including Lucerne, and even without my knowledge. So, you know, they really wanted to challenge it. They couldn't believe it. And so they had a different institute evaluate this. And these are the results. So they had the press release and it said more green for everyone. How is this possible? By not wasting green time, okay? That's all. We're using green time for who needs it at one time. And here you can see the improvement. So they had a system before that produced green waves, imposed green waves on the system, but long waiting times, as you see with the red areas over here, and the new self-controlled solution has a lot less waiting times. It does have green waves, but much less regular green waves, okay? But why do they have to be regular? Okay, so basically, the conclusion is we cannot control everything top down, in particular if we are faced with NP-hard problems. Now, I'd like to enter the question of network interactions. The world gets networked ever more every day, and in these systems, we cannot expect that intended effects would automatically happen. In many cases, there are side effects, there are feedback effects, there are cascading effects. One famous example is, of course, the financial crisis, and when Lehman Brothers went bankrupt, basically caused a bankruptcy cascade of hundreds of banks, and that costs us hundreds of billions of dollars for which you're paying your taxes, you know? This wouldn't have to be this way. So far, we have looked into interactions between system elements and how to change them in order to get another outcome that we like. Now we'll be looking into the effects of network structure. And let's start with logistics and supply chains. We have come up with models for those. And they allow us to take into account also network effects. So it's not linear supply chains. It could also be any kind of input-output system. And as you can see over here, there are three possible solutions, and they really depend on the mathematical properties of the input-output matrix, nothing else. So it's a network structure that determines whether we have damped oscillations and go to an equilibrium, or overdamped behavior, go to an equilibrium as well without oscillations, however, or whether we have growing oscillations. And that would cause booms and recessions, right? Now here is a more theoretical system where we've looked into three different supply chains, one linear, one that looks like a ladder, and one which is a hierarchical system. And we have assumed variations in the consumption. And that basically creates instabilities in the supply chain. And as you can see, those can be quite large. For the linear chain, this is what we get. For the hierarchical system, this is what we get. And only for that ladder over here, we get that a system where basically the oscillations are damped out, a system that behaves stable, as like it to behave. Why? Because there are alternative delivery routes. And as it turns out, this is exactly what, for example, Intel Technologies has been doing in order to get their supply chains stable. They did that based on their experience. I showed you the theory of that, okay? Now, power grids is a system that many people are talking about because people are afraid of blackouts. And in fact, blackouts have happened several times in past years in Europe, in Spain recently, but also in Germany. When they were transferring a ship, they had to switch off one line. And of course, they have been simulating the situation before. But what they didn't anticipate that on top of it, there would be one other line that basically failed. And that triggered a cascade with blackouts in many places all over Europe, thousands of kilometers away. And this is something that people have also been interested in looking into to understand those cascading effects that could cause blackouts. And here's a work of some colleagues who have been simulating such processes. And here, blackout will start around Spain, but the worst effect will be in Eastern Europe, which is pretty unexpected. So what can we do about it? Because everyone is very concerned. Our civilization very much depends really on power grids and their reliability. And another colleague has been looking into this, into the question, how can we improve resilience of systems by just changing that network a little bit? So to make minimally invasive changes in order to have a maximum increase of resilience. Okay. Now, perhaps more surprising is what happens in opinion formation. Now, many people are using social networks to share their opinions. And we've been interested in how does the outcome, particularly opinion diversity, depend on the network structure. And it turns out scale-free networks are pretty bad for opinion diversity, and therefore also pretty bad for democracy. right? Which is a pluralistic system. What Strogat's networks, on the other hand, can actually improve opinion diversity. I'll show you a video, and that video really makes clear how big the difference can be. So the graphic on the top shows diversity for a scale-free network, and you see diversity of opinions is pretty low most of the time. Plus, there's very strong changes in the system quickly. Like this system behaves like mad, like real social networks, basically, you know? And down there, this oversimplified, but what Strogat's network, you can see we have a high level of diversity and pretty stable, okay? So it shows us really that even without talking about content, I mean, what kind of posts people share, and network structure already determines whether the outcome is democracy or not. And social networks, if you design them badly, basically will destroy democracy automatically. Now, you understand this better if you look into properties of Powell laws. And what can happen is that either the standard deviation diverges, or in the extremist case, even the mean value diverges. I mean, they're not defined. Anything can happen in these systems, you know. This is how extreme those systems can be. So we have a mathematics to understand these kind of things, but therefore we should also pay attention to it, right? I mean, there's science that should inform us how to create good systems. For epidemics, unfortunately, we did make experiences recently. We've been working on this also some time ago. And if you had a globe where whenever somebody falls ill and gets the flu, say, a light flashes up. So if you had all that data and wanted to understand the spreading of the flu, unfortunately, you wouldn't understand much. You see this in this pretty widely scattered data cloud. Doesn't make much sense. And why is this? Is because of air traffic, okay? Because many people travel by plane. And if we come up, however, with a new effective distance that considers travel volumes between airports, so where two airports that have a lot of passenger traffic are close to each other in this new distance, then suddenly the spreading patterns make sense. Suddenly it's a circular spreading pattern, and we can actually predict which city will be hit by the flu next. We can prepare. And now we have a linear dependence, right? So suddenly we do understand the process. It does not even need big data, it just needs to combine two data sets and needs some scientific understanding of the spreading process of epidemics, okay? I will skip this video just to save a little bit of time. But it's also online. So what we do over here is we simulate the spreading process of a disease. Red are those who are infected, and you see most people are healthy here. Then we add shortcuts that basically infect people in remote places. And if there is a few shortcuts, then it does not change the situation much. But there is a point where suddenly things get out of control. So there's a critical density of shortcuts where basically you cannot stop the pandemic anymore, right? And perhaps most people would not expect that it happens out of a sudden. So there is really a critical point. Now, what happens for social cooperation? It's also very interesting. We're looking here at the system where people interact with their neighbors in a circle. And it turns out this is good for cooperation. It's a social dilemma situation we're looking at over here. And then we add some shortcuts again between remote people. And what we find is that as we increase the density of that shortcut network, cooperation goes up. It's a good thing. So you'd say, okay, let's connect. It's good for cooperation. And so we go up here. And then eventually, however, there's a point where things deteriorate. And in the end, actually, if everyone interacts with everyone else, there's no cooperation anymore. This is what we understand, because that's classical game theory. Social dilemma situation, we get this tragedy of the commons, no cooperation. The interesting thing happens between no interactions and infinite interactions. It's kind of in between, the magic happens, something else. In this case, cooperation. And we can use that. Here's another interesting example. So we've been looking into 4 different strategies interacting with each other. Cooperators, defectors, I mean, those who don't cooperate, and then moralists who cooperate but punish defectors, and immoralists who punish defectors but are still defectors themselves. That's why we call them immoral. It's a logical inconsistent somehow. Okay, and if everyone interacts with everyone else, then basically we end up again with the tragedy of the commons. I mean, no cooperation. This is what economists would predict based on the representative agent model. Now we'll simulate the same thing, the very same thing, same interactions, but with one difference, that people interact only with neighbors in a square grid. So we start with 25% of each strategy in the beginning. And then you see over time, the system changes quite dramatically, but we end up mainly with green. I mean, it's with moralists, cooperators who punish defectors, okay? So almost the opposite thing comes out just because of other interaction structures. So if we look at this again over here, and this is our starting point. Here, newspapers would scream, this is going to be the end of the world, everyone's going to defect, it's like hell. But then shortly later, actually, something else happens, right? And importantly, the defectors are separating the moralists from the cooperators. And this is important because the cooperators, if everyone interacts with everyone else, the cooperators crowd out the moralists because the moralists have additional punishment costs. Okay? So kind of the cooperators endanger their friends, the moralists, and once they disappear, basically the world ends badly. That was the scenario that I described before. But here, because the defectors separate the two groups, the moralists can survive, and they can spread because more successful as compared to the defectors. I know it's a bit complicated, but it's extremely interesting. So interesting that one of the most famous game theorists I know of, Herbert Gintis, couldn't believe it, And we were at the summer school and he was programming 3 nights in order to check my results. And then he had it. So kind of he confirmed that it was not a programming error. Okay. So there were really amazing things happening in complex dynamical systems, things that we can use for good. We can also use it in order to improve communication networks. So we've been wondering, what do we do if we have a blackout, okay? And we still want to communicate with other people. So we could try to create an ad hoc network between smartphones. And of course, there's mesh nets, but it turns out they're using up battery of your smartphone quickly. While typically it takes 3 days until you have government aid, like official help to save you. But this is the time within which most people die. It's basically, you could say most government aid comes too late. So basically in the first 3 days, you have to help yourself and your neighbors Can we build a system that does that? And exactly this is what we've done. We've come up with another protocol, what we call SOS protocol, and it's basically a hub and spoke network where we use those phones with a lot of battery charge as hubs to connect people with each other. And if they are then depleted of their battery charge, mostly, keep some of it for them, of course, then we switch over to other phones that have now the most battery, okay? And if we do this, actually, it turns out that we have a much better performance, and also the network looks quite different because we can avoid holes in that ad hoc network that would basically disconnect parts of the network. We can keep almost everyone on board for 3 days. Right, that is a mesh network, and it works for some time, but then it's quite bad. And this is our approach, the SOS approach. So here is a graphic where you can see mesh is basically running out of battery quickly, and the SOS approach, based on game theoretical cooperation, is actually outperforming that other system. Now, of course, we are now entering the time of big data. We are already here, and it's almost, people are talking about other things now, but it has an impact, of course, on agent-based modeling as well. So there's lots of data, at least for some companies, military, secret services, they're swimming in data, basically. In science, it's more difficult to get access to those data sets. But anyway, so we can think about it and talk about it. And the idea has been that we could now create a digital twin of the world. Basically measure everything and then, create a copy using machine learning to understand how the different parts interact with each other. So just to let you know, if you were not aware of this, there are systems where you are part of that digital twin. So there's an agent that simulates you, and it's personalized with the surveillance data that has been collected about you. And this is how they're simulating the entire world and preparing for wars and psyops, psychological operations, and so on. But anyway, the idea was, and that's the justification, couldn't we now see what's wrong in the world, see the problems, and basically fix the system where it's broken? It sounds logical. It sounds even easy. And therefore, also people are going even a step further and say, oh, couldn't we actually create a new operating system for society? Basically replace governance, politicians, administrations, replace everything by huge, powerful AI systems that know everything about the world, So there are some people working on operating systems, not just for smartphones and computers, but for the planet. You should know that, okay? Now, traditionally, a science-driven approach has been more or less this. So there's been doing measurements, making observations, or even doing experiments. With this, we've developed theories, we've modeled those systems, we've then calibrated them, fitted the parameters, we did some validation, we formulated hypotheses and then verified or falsified them. And once we were sure enough of the model that it's accurate enough for the purpose at hand, we were starting to do applications. And we could, for example, modify the kind of interactions or the network structure. Now, some people have simplified this process, and of course, simplification has benefits, makes everything more simple. And this is a data-driven approach which just takes big data, and puts that into huge machine learning system. And that's what's called often black box modeling with lots of parameters, like what I showed you before is few parameters, physicists have typically set with 3 parameters. You can fit everything with 5 parameters, so you make elephant wiggle its wing, its tail, and with a million or a billion parameters, what could you do? Okay, so basically you jump over a couple of these processes and make things very efficient, but how well does it really work? So for example, do we really do validation to the extent we should be doing it? And here's just an example. A colleague of mine has been using machine learning in order to come up with a prediction of trajectories of pedestrians. Of course, using a lot of parameters in these machine learning models, you can predict trajectories much better than the social force model, for example. But it turns out, even though those trajectories are much better fitted, they often fail to avoid collisions. Like the most simple and the most important thing, they fail to do. So they don't understand the process. They don't understand the system. So importantly, digital twins, they work for infrastructure, they work for production systems and so on pretty well, for architecture, but for living systems, for societies, for people, there's often complexity science missing. So the black box approach has some limitations, and there are many of them. I won't read them all. Among them, it's the complexity of the system. Just take this example, the game of life, based on 3 simple rules of a cellular automata. Yeah? It can produce non-repetitive dynamics, looks already quite complicated. You can use that data, feed it into a machine learning model, say with 1 million parameters, and you can approximate this dynamics, no question. What will not get is those 3 rules, unless you help the system. Okay, so basically, it's difficult to reconstruct the simple rules that may be behind a complex system. And so besides the black box AI approach, there's another scalable modeling approach that the Future ICT project that was mentioned before was willing to take. That was basically worldwide open source modeling combined with explanatory models and machine learning, right? So explanatory models, I think, is important. And now, of course, we're entering not only the age of big data, but the age of generative AI. And here agents are being equipped with neural networks. So agents are not dumb anymore. They have a little brain, they can learn. And they can do all sorts of things. And that brings us to agentic AI, of course, very interesting technology. But it also will make crime scalable, will make war scalable. And the question is, what will win, the good people or the bad people? And how many accidents will happen on the way? Anyway, the vision is already to replace politicians by AI systems. And not only politicians, also to replace you. And this is what they call, in the smart city charter, what they call post-decision, post-voting society. The idea is, if those systems know everything about you, why should they even ask you? Okay, the issue is those LLM agents do not represent human diversity well. They go for the mainstream, and they don't do what people and societies do. But just imagine the military would not have just ChatGPT, probably have something 100 times, 1,000 times, 1,000,000 times more powerful. I don't know exactly, right? Well, what could that be? Basically, not only feeding all the text you can grab into the AI system, not only all the pictures, but also all the Internet of Things data. Plus, we are now in a time of converging technologies where nanoparticles can be read out in order to get even more data. So basically, we have a global scale detailed measurement down to the cellular level. This is where we're heading. Now feed all that data into an AI system and let it generate the next step in human history. So it's a history machine that produces our future. And how much do you have to say in that system? Anyway, some learnings. Everyone, I think, is in favor of responsible innovation, but this requires to understand the impact of technology on society. A precondition for this is the understanding of emergent properties and phenomena in complex network dynamical systems. There's probably 0.0001% of people on this planet who know something about complex dynamical systems. Most politicians don't know it. Most managers don't know it. How can they do responsible innovation? You know, we should give courses on complex dynamical systems, and that's what I'm trying to do. Complex dynamical systems such as humans and societies cannot be well represented by black box machine learning approaches. That's my personal point of view. So would it create a realistic digital twin or rather deep fake? I think there's a chance that it could be deep fake and we could not even tell the difference because it looks so realistic. So basically we would be unable to fix it. Agentic AI is coming and it's going to have great applications. We can make billions with it, but there are also dangers. Generative AI agents are here, but do not represent human diversity well. So we should not hand them over decision power, too much decision power, I should say. Democracies have already been damaged. I think also we've been overly optimistic about the brute force AI approaches, you know, the one with a nuclear power station in the back in order to simulate human intelligence, while a human brain can do it for 40 watts, you know, like almost nothing. So we've seen the DeepSeek shock on the financial markets. 1,000 billions were lost in minutes, and shows you the size of the hype and the bubbles that we have in the system at the moment. So we've wasted a lot of money. But you know, I'm in favor of digital technology. I just think we need to use it in a different way. We should use it for informationally assisted self-organization, support self-organization. And that would be efficient and resilient. It could handle reasonably large deviations and perturbations, and it would be compatible with freedom, democracy, and human rights. So why don't we do that? You know? Okay, besides interactions, network structures, even when interactions are not changed, can make a big difference for self-organization. So it can change the system for better or worse. They decide over cascading effects or not, blackouts or not, pandemics or not, disasters or not, cooperation or not, survival or not, supply shortages or not, circular economy or not, democracy or not, wisdom of crowds or not, truth or not. So let's make good use, scientific use of technology in favor of people and the environment. It will need you to come up with better solutions and systems. Change is coming. You should contribute to it. Be hopeful. Together we can make it. And there will be a new kind of civilization eventually, I believe. And so what can you do? You can apply a value-sensitive design approach built in the values of our constitution, of democracy, our culture into the system. So those technological systems don't destroy our society. Build democracy by design. Invent technology that protects human rights and the environment too. Create freedom tech. Replace the benevolent dictator approach. Kind of now we're going to optimize the entire system, impose the one very best solution on the world, no matter whether people like it or not. And of course, there is not just in an evolving system, there's not just one solution. It's really the root of totalitarianism, the idea that you could optimize society. So get rid of this idea of the benevolent dictator and replace it by assisted self-organization, co-evolution, and boosting serendipity. That's it. Thank you.
Thank you, Professor, for the fascinating talk. I really like the principles that you've brought about. One thing I was curious about is there are many things that we don't understand, and you showed a lot of use cases for these complex network dynamical systems. So if there's a problem at hand, do you see some features of the problem which could indicate to us that these sorts of problems, this can be a good scientific method to apply versus like trying to filter out the problems which can be answered by such thinking? Do you have any suggestions or ways to look about it?
Yeah, it really depends on the question. Do you have a system where you have many components, where each component basically adapts to what the other components do, right? This was kind of characteristics for the systems I've been talking about, but there are a lot of those systems, from our brain to society to financial markets to traffic to and one important point I didn't mention so far is, in order to build a society that uses this wonderful self-organization, we need modularity. The least thing I would do is to couple every element of this world with every other element. But this is what this history machine actually does. It feeds in all the data of the entire world, and everything gets connected. And so it's prone to cascading effects, I think. It's prone to these butterfly effects. So I think we really need to have a different design approach. We need decentralized systems. And they have many benefits. They also have some challenges, more difficult to create. But on the long run, I think we'll find out they're more resilient and they're also less prone to power abuse.
Thank you. Okay. Over there. Come on, please.
Thank you very much for a really interesting talk. I just have a very random thought, and it might be a weird question. I was just wondering if science and knowledge itself is just a result of chaos. And, considering we are a group of researchers that have a limited range of vision, and we are trying to best inform our decision on what we do and what type of results we produce. And at the end, what becomes an accepted norm that we call knowledge is just, what came about and how much we can trust that.
Mm-hmm. Yeah, it's a very good question, like the process of figuring out truth. And what I'm concerned about now is that we're using, or some companies are using AI to boost certain subjects, like AI itself, right? Because you can make billions on that, but it will distort our perception of the world, right? What if those big AI systems that have the nuclear power station in the backyard, if they're not the solution for everything, you know, and we can't see those alternative solutions anymore. Yeah, this is what I'm concerned about.
Thank you. One last question here.
Yeah, thank you for the talk. I was interested in the slide about the destruction of cooperation when there is some interactions. And if you can come back to this, because I was struck by the figures that were on this diagram, because to me,
This one?
I don't know. Yeah, this one. Yeah, and the scale looks frightening because it's a few tens of persons of connection density that would destroy the cooperation. Is that
Yeah,
the case?
it's less connectivity than you'd think could start the process of undermining cooperation. Yes.
Okay. So you confirm this, really?
I think it makes sense, you know, you know the this principle of being connected to everyone on the planet over 6 nodes,
Yeah.
right? And if you consider this, then it does not take many shortcuts in order to have a systemic impact. Yeah.
Okay, that's thank you.
All right, so let's recover from this talk, and I trust in you that you'll fix the problems ahead of us, okay?
So
Thank
thank
you.
you very much.